The whole process of graphing rational functions involves fundamentally identifying horizontal and vertical asymptotes and then just plotting a few points around them to discover the behavior of the graph. Let's go through the whole process here with this function. Now, we begin by identifying asymptotes, and we think to ourselves, well, let's identify a vertical asymptote here. The zero of the denominator is -4. So we have a vertical asymptote at -1, 2, 3, 4. And we'll draw that asymptote. And now we look for the position of horizontal asymptote by looking at the degree of the numerator and denominator. We see that the degree of the polynomial in the denominator is larger than the degree of the polynomial in the numerator, and so our horizontal asymptote is simply the x-axis. Now, it really doesn't show up very well if I make a dotted line here, but let's just realize that it is the x-axis, the line y equals 0. Okay, with that in mind then, we want information about the graph on either side of this vertical asymptote. So we'll just make a table of values and find points associated with an x of negative, let's see, 1, 2, 3, 4, -5, -6, -7. That's what I'd like on this side. And on the other side, I'd like -3, -2, and -1. So I've done that here with this table, -5, -6, -7, and these are the subsequent y values. Let's plot them. -5 goes to -2, -6 goes to -1, -7 goes to -2/3. Now all we're doing is kind of establishing the distance from these asymptotes where the turn is made. We know what's going to happen at the extremes of the coordinate plane. The graph is just going to get really close to those asymptotes. So we just establish this curve and then draw the graph so that it snuggles up to the asymptotes. Now let's see what happens on the other side. It'll be a similar kind of behavior. We have, let's see, -3 goes to 2, -3 goes to 2, -2 goes to 1, and -1 goes to 2/3. And so on this side, the graph will do this. And that's really all there is to it. The process is identify asymptotes, plot a few points, draw the curve, make that curve snuggle up to the asymptotes, and we're home free. Let's look at it on the calculator. Let's take a quick look at the graph of this function on the graphing calculator. I've entered the function here, and on standard settings, the graph looks like this. I notice that the calculator seems to be constructing the graph of the vertical asymptote. Actually, what's happening is that the calculator is connecting a point which is way down here, just to the left of the vertical asymptote, but off the graph, with a point that's just to the right of the vertical asymptote, but way up here off the graph. And the reason that the calculator is connecting those two is because we're on the connected mode, which means that the graphing calculator is just connecting f of one point after another that it is calculating by stepping from one point to the next. And the calculator is not stepping right on x equals -4, so it's just connecting the dots for f of the point just to the left of -4 and f of the point just to the right of -4. Well, there are two ways to deal with the situation. If we press mode, this is the menu that shows up, and if we go down here to where it says connected and dot, now we're on connected mode right now, and if we go over to dot and press enter and then go back to the graph, we'll see that the graphing calculator is just placing a dot for f of each x value that it's stepping on. So the dots are not being connected here so much as they were before. Well, this seems to give us a rather incomplete graph, though. So let's go back to mode, cursor down to connected, and put it back in the connected mode. And here's the graph then once again. The other way to deal with the situation is to establish some friendly settings here so that the graphing calculator is caused to find f of -4, and it will find that that value is undefined, and therefore the vertical line will not be drawn. So let's go to the window settings, and friendly settings, you recall, were those that are integer multiples or divisors of 9.4. And I'm just going to enter -7.4 here, and then for x minimum, and for x max I'm going to enter 2. Now that gives a total horizontal distance of 9.4. The graph looks like this. By the way, I'm not so concerned with a square perspective here as I am just getting friendly settings. Now notice that the vertical, what looked like the vertical asymptote before, is simply not on board. Now we can see more clearly what's happening by pressing trace and then tracing to the left. I'm going to simply trace over or cursor over to where we have -4. Notice that there's no y value here for an x of -4, and that's exactly what we would expect to happen. Even though the functions may get a little more complicated, the concept for graphing is exactly the same. Identify positions of asymptotes and plot a few points around those asymptotes. Here, for example, we look at our function, and to identify vertical asymptotes we need the zeros of the denominator, so we'll factor the denominator first and then identify the zeros of the factors. This factor becomes 0 when x is 3, and this one when x is -2. So we have a vertical asymptotes at 3 and -2. So we go over to the graph, and at 1, 2, 3, a vertical asymptote. And then at -2, another vertical asymptote. Now, for the horizontal asymptote, we look at the comparison of the degree of the polynomial in the numerator versus denominator. Now, they're the same degree. They're both second-degree polynomials. So we know that the horizontal asymptote is a y-line which is equal to leading coefficient over leading coefficient. So it would be y equals 2 over 1, or simply y equals 2. So we have a horizontal asymptote going through here. Now notice that the two vertical asymptotes seem to subdivide the coordinate plane into 3 regions. And we just like to know the behavior of the graph in each of those 3 regions. And to find that, we simply plot a few points in each one of the regions. So we want some points out here. Well, those would be x's of -1, 2, 3, 4, 5. -3, 4, 5. And then in here we want x to take on values of -1, 0, 1, and 2. And then out here 4, 5, and 6. Now I've made such tables of values. I've made a little table of values for the left-hand part and the middle part and the right-hand part. Let's see what happens as we plot these points. -5 goes to 2.1, -1, 2, 3, 4, 5 goes to 2.1, and immediately we are discovering that the graph in this region is going to be above that horizontal asymptote. So it's going to take a curve like this, and it's just a matter of where the curve takes place. That's all we're discovering here by plotting these points. The next point is -4, 2.3, -4, 2.3. Then -3 goes to 3, and the curve looks like this. To get a better idea of the curve, you could pop it onto the graphing calculator if you want to. Now, for the middle part, the middle part, by the way, can have a lot of different behaviors. We could have kind of an S pattern here. That is, the graph can go through the horizontal asymptote when we're kind of in the middle of the coordinate plane. So we could have an S pattern like this, or an S pattern this way, a U pattern up, or maybe a U pattern down. So it's kind of all over the board. Let's see what kind of pattern we have here. Now these are the coordinates of points that are in the middle. So let's see, -1 goes to -1/2, -1 goes to -1/2, and 0 goes to 0. 1 goes to -0.3, 1 goes to -0.3. 2 goes to -2, and it looks like we have kind of a downward pattern here. That is a U down kind of thing. So the behavior of the graph looks about like this. Now, for the other part, for this part out here, let's see. We plot some points over here. 4, 5, and 6. 4 goes to 5.3. 4 goes to 1, 2, 3, 4, 5.3. And 5 goes to 3.6. 1, 2, 3.6. 6 goes to 3. And now we know how the curve behaves. So there's our graph. Here's another one. The approach is exactly the same, and the trick here has to do with the horizontal asymptote. Now, first of all, let's identify a vertical asymptote. The 0 of the denominator is simply at x equals 1. X equals 1, that's right here. And now we look for the horizontal asymptote by looking at the degree of the numerator compared to denominator. So now notice we have a second degree numerator, a first degree denominator. So the degree of the numerator is larger, and that means we don't have a horizontal asymptote at all. We have a slant asymptote. But let me show you how to find the equation for the slant asymptote. That equation is found by simply performing the division that's indicated here and taking sort of the whole part of the whole polynomial part of that without the remainder. Here's what I'm talking about. I want to take this polynomial and divide by this one. I could use long division like this and go through the process, or I could use synthetic division by thinking, well, if I'm dividing by x minus 1, then synthetically I'm dividing by 1. And now I use the 1, and the negative 3 here. And remember the process, bring down the 1, 1 times 1, 1, together 2. 1 times 2, 2, together negative 1. That's the remainder. And what I want is the polynomial described by those two items. And that polynomial is simply 1x plus 2. So the line y equals x plus 2 is a slant asymptote. So we can come back over here and draw that line if we want to. Now, notice it's in the slope-intercept form for a linear equation. And the intercept is at 2, and the slope is 1. Now, for a slope of 1, that's a rise of 1, run of 1. And from this point, rise 1, run 1, and so on. So we have points out in this direction. And then in the other direction, we can generate points as well. Now, the dotted line then describes our slant asymptote, and if we plot a few points, we'll understand the behavior of the graph around these asymptotes. Let's see what happens. I've made a table of values here, and 0 goes to 3. Oops, 0 goes to 3. I knew it couldn't possibly be right on top of the asymptote here. 0 goes to 1, 2, 3. And negative 1 goes to 1.5. Negative 2 goes to 1/3. And you see the graph is just kind of real tight on the asymptote here, and then it's going to just blast upward here. And we can go ahead and graph that because my other 3 points are on the other side of that vertical asymptote. So I know that on this side, this is what's happening. And I get closer, closer, closer as I go out this way. All right, 2 goes to 3. Then 3 goes to 4.5. We're getting tight on that asymptote already. 4 goes to 5 2/3. So it's kind of like this. Now notice that they look to be really close on that asymptote, and then the turn is made and it just kind of drops down like this. So the graph looks like this. Let's take a look at this one on the calculator. I've already entered the function, and notice that I have contained the numerator within parenthesis and the denominator here within parenthesis. And I've also made window settings that are a little bit creative. The x minimum and maximum are at the friendly settings, but for y minimum I set up negative 3 and y max 7, so that the graph has more of the appearance that we might expect from what we saw on the board earlier. And the nice thing about looking at a graph like this on the calculator, there are several things that are kind of important to us, or could be important to us. Notice the setting here above graph. It says table. Well, if I press second and then that button, I can actually show a table of values for this function and for the plotting. If I'm using a point plotting method, and that of course is what's going on within the calculator, then 0 corresponds with 3 here, and 1 is an error to the calculator. There is no definition for x equals 1 because it causes an undefined situation, and that's where our vertical asymptote was. And we can see that 2 goes to 3, 3 goes to 4.5, and so on down the line. In the negative direction, if I just cursor up far enough, we can get to the negative values of x. Here we go, into the negative values. And so we have a built-in table of values that we can look at, and we can verify some of the things that we find manually by using this kind of option. And another idea, I'll go back to the graph for a moment, but another idea that we can use in the graphing calculator is that we can verify our slant asymptote. We could go back, for example, and enter the slant asymptote. Remember, it was y equals x plus 2. So if I enter y equals x plus 2 and then graph, sure enough, I can see that the graph snuggles up to the slant asymptote at the extremes of the coordinate plane. To construct the graph of this function, we can actually use two methods. One is the point plotting method, and to use the point plotting method, we would need to rewrite the expression on the right side of the equation as one single fraction. So to do that, we'll rewrite the 1 in terms of our common denominator x minus 3. So we'll rewrite 1 as x minus 3 over x minus 3. Now we can bring the fractions together, and in the numerator we collect the constants. So we have x minus 2 over x minus 3. Now what we want to do is identify vertical and horizontal asymptotes, and for the vertical asymptote we look in the denominator and we decide what value of x will cause this denominator to become 0, and that of course is x equals 3. So the line x equals 3 becomes our vertical asymptote. For the horizontal asymptote, we look at the coefficients. Actually, we look at the degree of the numerator and denominator first. Those degrees are the same, and therefore, to identify the horizontal asymptote, we form a fraction composed of the coefficients of the leading terms in the numerator and denominator. Here, they're understood to be 1s. So it's the y line, y equals 1 over 1, or simply y equals 1. Well, now we're ready to build a table of values. Now we'll select values to the left and right of our vertical asymptote. So to the left of the vertical asymptote, we might use these x's. To the right of the vertical asymptote, we might use these x's. And now we would simply evaluate the expression x minus 2 over x minus 3 in terms of the x's that we've chosen. And we would get these subsequent y values. Well, we'd probably want to rewrite 3 over 2 as 1 1/2 and 4/3 as 1 1/3. And now we're ready to plot some points. The points to the left of the vertical asymptote are in these positions, and then to the right of the vertical asymptote we'll plot those points as well. Now all we're doing is figuring out or finding by plotting these points near the vertical asymptote is the behavior of the graph in this portion of the coordinate plane. After all, we know that the graph will approach the asymptotes at the extremes of the coordinate system. So now we can construct our graph. Now, as was mentioned earlier, we can actually use two approaches to get this graph. Let's look at the other approach now. It's actually a transformation type of idea. And let's look at the notion of transformations when it comes to rational functions. Let's take a rather primitive rational function like f of x is 1 over x, and here's its graph. Now consider a function g of x, which is 1 over x minus 2. Do you see that we have vertical distances, you see, for f of x, and all of those vertical distances will be dropped 2 on the coordinate plane. So here's the graph of the g function. Now let's consider another g function. Suppose we're talking about 1 over x minus 1. Now, of course, we can think of the x minus 1 as subtracting 1 before we perform this prevailing operation of taking the quotient, you see. So in this way, we can think about a horizontal movement in a direction we don't expect. So we would move the graph 1 position to the right on the coordinate plane. Well, now let's go to our original function. We have both of these elements involved, that is a horizontal and a vertical movement of a fundamental graph. The x minus 3 in the denominator would cause the graph to move 3 positions to the right on our coordinate plane, and then of course the plus 1 would cause the graph to move up 1 on the coordinate plane. So here's the graph, and it certainly is a graph that we solved earlier or found earlier by using the point plotting method. A utility company burns coal to generate electricity. The cost of removing a certain percent of the pollutants from the smokestack emission is typically not a linear function. That is, if it costs, let's say, C dollars to remove 25% of the pollutants, it would cost more than double that, or 2C dollars, to remove 50% of the pollutants. As the percent of removed pollutants approaches 100%, the cost tends to become prohibitive. Suppose that the cost C of removing P percent of the smokestack pollutants is given by this equation. C equals 80,000 P over 100 minus P, where P is a number between 0 and 100, and it can't be 100. You see, P cannot take on the value of 100 because the denominator would become 0, and therefore the equation undefined. All right, let us sketch the graph of this function. Now, I've already entered the equation onto the calculator. It's important to understand that x is playing the part that p plays in the equation. So x corresponds with p, and y corresponds with c. So x is some percent of pollutants removed, and y is the cost of removing those pollutants. Okay, the window settings, I have looked at this before, and so I have made my settings accordingly. I set the x max at the point where the function is undefined at 100. I backtracked from there. 94, you know, is the magic number for horizontal distances to have a friendly value when we use trace, and we're going to use trace in this problem. So I backtracked 94 from 100 to get 6 as the x minimum. The y minimum now, that's a cost figure. Y is a cost figure. I set up the minimum at 0 and the max at 1 million. And here is the graph. Now I'll press trace, and let's understand what this sort of means, what the x and y components mean. I want to make sure we understand that before we get into our problem. An x of 60 means that we have we're removing 60% of the pollutants, and a y of 120,000 means that it cost $120,000 to remove 60% of the pollutants. All right, let's propose a problem. Suppose you're a member of a state legislature and you're considering a law that would require utility companies to remove 90% of the pollutants from their smokestack emissions. If the current law requires 85% removal, how much additional expense would the new law ask the utility company to spend? Well, this is just a matter of tracing to the proper points on our graph. You see, the current law says that we are requiring 85% removal of pollutants. So let's see how much that's costing the utility company right now. Oh, it's costing the utility company this much money. Well, that's $453,333 to remove 85% of the pollutants. Now, if we want to pass legislation that is asking for 90% removal, it's going to cost the utility company $720,000 for that. And the difference between $720,000 and $453,333, you see, would be the additional cost that we are bringing to bear on the utility company. And that difference turns out to be $266,667. So it's kind of important, if we are state legislators, to understand what we are going to cost that utility company, or what this legislation is going to mean in terms of cost to the utility company to implement our proposed legislation.